Hello students, welcome to the session on partition of sum of squares and the one-way ANOVA procedure as a part of the course Statistical Methods for Psychological Research Part 2. After completing this module, the students will understand the partition of sum of squares. They will come to know the one-way ANOVA procedure. They will also understand the concept of degrees of freedom. In this part, we are going to discuss on partition of sum of squares in one-way ANOVA. We shall learn whatever we have learned so far in the previous lesson, the notations used in one-way ANOVA, partition of sum of squares. As we all know, the one-way analysis of variance tries to find a relationship between a continuous dependent variable and a categorical independent variable with more than two levels. So, for example, if we have k independent groups and we wanted to compare them in terms of mean, we will use one-way ANOVA. So, capital K represent the number of groups to be compared. Capital Y bar represent the overall mean, which is the mean obtained for all the scores. Y1 bar, Y2 bar up to Yk bar is representing the sample mean of k independent groups. Yij is the outcome or response measured from the jth person in the ith group. For example, Y12 represent the scores obtained from second person in the first group. Mu1, Mu2, Mu3 so on up to Mu k is representing the population means of the k group. N1, N2, N3 so on up to Nk represent the number of observation in the first group, second group so on up to kth group respectively. So, when you add up all these sample sizes, you will get small n, which is the total number of observation in your study. So, in the previous lesson, we have learned what are overall sum variation, within group variation. So, we will just do a recap of all those concepts. So, within group variation is nothing but the amount by which the individual scores vary around the sample mean. So, we are very well aware of the mathematical equation which is given there. So, it is a natural variation, it does not reflect the difference caused by the group or treatment. So, within sum of squares is otherwise called as error sum of squares, usually find in a statistic textbook. So, that is represented by SSE, but for this lecture I am going to stick with the notation capital S in the subscript W. So, this means within sum of squares. Similarly, between group variation is nothing but the amount by which individual group means vary around overall mean. For 4 groups or up to k group, we have SSB, which is represented in the equation, and the overall variation is nothing but the amount by which individual scores vary around the overall mean, and again the expression is given over there. Now, let us understand how the partition of single observation is going. For example, if you measure a single observation from a sample, this constitutes a different component. So, it is composed of grand mean, treatment effect and natural variation. Treatment effect means the amount by which the population mean deviates from the grand mean. So, we have Yi bar minus Y bar. Similarly, grand mean means mean of all scores irrespective of the group represented by Y bar. Natural variation is everything which is left over when you subtract from grand mean treatment from capital Y, that means your observation. So, the partition will go like this: capital Yij is equal to capital Y bar plus Yi bar minus Y bar, that is the deviation of group means from the overall mean. The second component is Yij minus Ya bar, which is the natural variation. Why we call it as a natural variation is, even though you give a same treatment to a set of subject, they naturally vary in their response. So, that we call it as a natural response or natural variation. So, the first component Yij is a response, Y bar is grand mean, treatment effect and then natural variation. So, we shall rewrite this equation as bring your capital Y bar to your left hand side, so that we have we will be able to get the overall variation when we sum it up. So, this can be divided into two parts, which is given in the right hand side of the equation. So, the various effects are additive in nature by looking at this equation. So, we will discuss further on this. So, for example, consider three set of scores. Consider this hypothetical example where we have three groups and three observations each. So, in the first group we have 1, 2, 3, and in the second group we have 4, 5, 6, and in the third group we have 7, 8, 9. So, the mean of the first group is y1 bar, which is 2, the mean of the second group is 5, the mean of the third group is 8, and the overall mean is 5. Now, we try to understand how this partition is working. So, we will substitute all the quantities from this small set. So, Yij is, for example, I wanted to find out what is a partition that we are getting for the observation 3, which belongs to group 1. So, Yij is 3 and the overall mean is 5. So, I have written 3 minus 5, which is equal to Yi bar is the observation correspond to the first group. So, the mean of that particular group is 2 minus the overall mean is 5. The second quantity is Yij, again 3 minus Yi bar is mean of that particular group. So, that is why we are getting 3 minus 2. So, with a simple computation we may end up with minus 2, which is equal to minus 2. So, thus we are proving that this partition work for every single observation in the set of samples. Let us try to understand this partition of observation or the partition of variation through the above example. Let us rewrite this term as given there, Yij minus y bar, which is equal to the right hand side. We are just going to take the square on both sides. So, when you take the square of the right hand side, it will be like a plus b the whole square. So, here when you expand a plus b the whole square, we will get a square plus b square plus 2ab. Here the 2ab square is missing because we know that the sum of deviation of the score from the mean will be 0. So, because of that reason we have the ab term is vanishing. So, we have a term and b term. Now, we are going to apply sum over all the observation, that is j ranging from 1 to ni. So, throughout the equation we are going to sum, that is ranging from 1 to ni, and then we are going to again summing over all the groups. So, previously we have summed over all the observation, now we are going to sum through all the groups. So, now we have two summation, one summation ranging for the observation and the other group summation for the observations. So, here we have the left hand side term what is called the total sum of squares, and the sum of squares of deviation of individual group mean from the overall mean stands for the between sum of squares, and the sum of squares of deviation of scores from the group mean will be within sum of squares. So, this is the reason why we are calling this one-way ANOVA model is a additive model, because the various effects here are additive in nature, that is our treatment effect and the natural variation. So, here this splitting of total sum of squares is referred to as partition of sum of squares. Now, we are going to represent the total sum of squares for our discussion as capital S to the subscript t. Degrees of freedom is one of the important concepts in one-way ANOVA. Let us try to understand what is degrees of freedom, which is abbreviated as DF in many textbooks. So, it is defined as the number of observations which are free to vary. For example, in a class if there are 10 students, so today it is a birthday of one student, so he wanted to distribute cake to all of the students. So, he is bringing 10 pieces of cakes. So, when he try to distribute to the first person, so the first person is having the full choice, so he may be free to choose any cake out of 10. Now, if we move to second person, the second person is having only 9 cakes which he is free to choose. So, similarly, when he tries to complete at the last person, there is no choice, he has to take only the last piece which is left over. So, what is the total number of observation which is free to vary is only 9. So, that is a concept of degrees of freedom. So, whatever sample size we have, that is n. So, n minus 1 will be the degrees of freedom. So, n minus 1 scores or observation which are free to vary. Now, let us understand what is the degrees of freedom for total sum of squares. So, altogether, irrespective of the group, you have small n observation, that is sum of all the scores in the all groups. So, it is n1 plus n2 up to nk, which is total n. So, the degrees of freedom related to total sum of squares is n minus 1. The degrees of freedom for between sum of squares is, so between means we are trying to find or we are trying to compare treatment. So, we have k treatments. So, how many treatments are free to vary? K minus 1. So, where k is the number of groups or treatment. Similarly, we try to understand what is the degrees of freedom for within sum of squares. So, as we said, the single measurement or the variation or additive in nature, the degrees of freedom is also additive in nature. So, we can obtain or derive the degrees of freedom for sum of squares for error, that is within sum of squares, by subtracting the between degrees of freedom from the total degrees of freedom. So, the total degrees of freedom for error is nothing but n minus 1 minus k minus 1. So, from a simple mathematical calculation, we will end up with n minus capital K. So, which is the degrees of freedom for error. In this video, we have learned about what is partition of sum of squares in one-way ANOVA and what is degrees of freedom related to one-way ANOVA and how to derive them for various sum of squares in ANOVA. We will continue in the next video. Thank you.